So now that we have this idea of what contents we would need with metadata, under metadata, and how would we organize things and into our file system. Next, let's move on to how we would organize the files. The file organization. Now this should be very simple, right? We know that we have this inode that actually stands for index node. In different file system, people call this struct that stores all the metadata about where the file is located, how long the file is, when the file was last modified, things like that. They call with different names, like dnode, inode, but let's stick with inode. Again, that's just the terminology, but you get the meaning of what do we mean by when we say that, what contents do we store inside the inode. So we have this inode, and then every inode is identified by a unique inode number. This inode number is low-level name of file. And from this inode number, the location of exact data need to be calculated. Because once we know this inode number, then we should know where the file to which this inode number refers to is stored in the data block region. How do we calculate that? Any clues? Any thoughts? Again, let's rely on the basic math. So let's say that, for example, to read inode number 32, file system would first calculate the offset into inode region. So if we want to read inode number 32, first we should be able to find where this inode number 32 is located, right? So now we know that, now we know the number, inode number of that, and let's say that they're stored in sequential fashion. Inode number 0, then number 1, number 2, number 3, until we can have at max 80 inodes into our inode, the blocks reserved for inodes. So in order to go to this inode number 32, we could do simple mathematical calculation, right? Like 32 multiplied by size of inode for the system. And let's say the size of inode is 256 for us. So then it's 32 into 256. That would give us 8 kilobyte. And now we know that we don't start into the fashion how we organize our content on our disk. We don't start inodes right from the block 0, right? Our block 0 is reserved for superblock. Block 1 and 2 are reserved for allocation structures, and then we start inode from block 3. So definitely we would need to add that, add it to add the starting address of inodes to this. And because each of our block is 4 kilobyte, and if the starting address of the inode is 3, then 3 fours are 12. So then our starting place of inode would be 12 kilobyte, and then we add that, so that's 8 kilobyte. So we know that at the location of 20 kilobytes, that's where our inode number 32 would be located, just tracing it from the beginning of the disk. Now, if the disk sector size is 512 bytes, so then we would have to go to, I have to change to another page. So then we would have to go to this 20 kilobyte because it's kilobyte 1024 multiplier. And if the disk sector size is 512, that means the sector on the disk that we have to look to get to this inode number 32 is 40th sector. So generally speaking, block could be identified as formula. Inode number multiplied by size of inode divided by block size. And to identify the sector number that we have to look into the disk, we can generalize the calculations that we just did above with our example and see that the formula is block multiplied by block size plus inode starting address divided by sector size of the disk. So this would give us to which sector should we look. Now, we know where to fetch information about this inode number 32, but still we have not quite solved our original question, right? How do we use this? How do we read the information from this inode struct now at this location and reach to the actual file that we want to read? The file about which this inode number 32 is about. So the big question is still standing. How inode refers to where data blocks are. Any thoughts about how could we do this? I would ask you to take a minute and think of this. Okay, so I hope you have already thought of the solution to this question. If your solution is, well, that's straightforward enough, isn't it? I don't need a minute. I have it right off my head. Just use direct pointers. Then you are correct. So we could use direct pointers where each inode struct has this pointer to the location where the data about this file is stored. So each inode has one or more direct pointers. Now, why did I mention one or more? Think of it. This pointer points to the disk address. Why do we have one or more? Well, how do we know that the file that we want to access can exactly fit inside a single block? We do not know that, right? So if these pointers are pointers to the block that is storing this file, then we do not know that this file will just be big enough to fit only inside a single block. This file could be a bit more bigger to span across multiple blocks. And that's where we might need multiple pointers. So we know that, okay, this file that is like the inode that's storing information about this file. This file is spanning across first over like the first pointer that reads the first part of the file, the second pointer reads the second part of the file, and so on and so forth, depending on the size of our file. Do we see any problem with this approach? Nah, looks pretty good, right? Okay, let's just close it. Hey, we are done with our file system implementation. But if it's that good, then we would be using this knife file system even in our today's life. Probably we do not. Look into the current file system that you have on your desktop or on your laptop. And I do not think if you dig your head inside the code of that file system, it's this simple enough. So what are we missing? What is the problem? I'm sure you're already thinking of this problem. With every new solution, there is a problem, right? And then we have solution for that problem, and that has another problem. And that's our design decision tree, which is very critical when we design any new component of system. So the problem with this approach of direct pointers that we could have inside inodes to locate to our files is, what if file is really big? What do I mean by really big? Bigger than block size. Multiplied by number of direct pointers in inode. So in that case, then we wouldn't have enough pointers inside inode to be able to point to the entire file. At a point, we would be just able to point to a part of file, but if the file is bigger than that maximum number of pointers we could store inside an inode, then we wouldn't be able to refer to that entire file. So can we just leave it as it is? No, then if the file is bigger and we cannot just say that, hey, because the file is big, you will be able to only access a part of file, and the file system is just not responsible to give you an entire file. Well, I wouldn't want to use such a system, or I wouldn't want to use such a file system where if my file is big, let's say I have this very important video of my wedding, and as soon as I want to access this video, it just says that, hey, you can only access the first part. As soon as the part of where mine and my husband's vows, like my favorite part, that started, it says, well, your file is bigger than this. Sorry, this file system doesn't allow you to access that. I would hate such a file system. So we cannot just lie low with this problem. We have to solve that. How do we solve that? Any ideas? Any suggestions? Query your inventory of different data structures. Maybe that could give some pointers to think of the solution. Well, one of the solutions that I could think of is using multi-level index. So let's say that we have an inode block. That inode block is storing all the information, and it's storing this list of pointers that points to this file, the location of the file block. And let's number them as file block. Let's say it's number 51. Then the second stores the location of the second file block, number 52. And at max, we have space only for storing 2 file blocks. Then at the end, I reserve some space into my inode. And this last pointer doesn't point to the rest of the file or the block that stores the next part of the file, but rather it points to a block, let's say still in our data block region. It could be numbered 53, doesn't matter. But what this block stores matters is it would be able to store list of another pointers. So now this block 53 does not store file detail, but what it's storing is pointers. So now just with the simple approach of multi-level index, where we have, this is the first level of index, this is our second level of index, right? We gained another certain number of pointers. So in the example that we just took in our, we could store maximum 80 inodes. So let's say if we could store, let's say that inode can have, we can take a specific example where inode may have certain number of pointers, for example, 12 pointers, and this single indirect pointer to the block storing rest of the pointers. So if the block size is 4 kilobyte, then definitely we can store into this additional block, we can store additional 1024 pointers. And thus now in total, we could store like the original, the pointers that we could fit into this first level, plus these pointers that we could fit into this entire new level. So then the first pointer of this new block could then point to the block which stores the third location of the data, like the third part of this file. So in total, the total number of supported files by such multi-level index is thus then increased from just the 12 to 12 plus 1024 additional pointers multiplied by 4 kilobyte. So that's around 4,000. To be accurate, doing the calculations in my calculator, not in my brain, it's 4144 kilobyte. So this is the maximum file size supported. Pretty huge, right? Much bigger than our initial file size supported. So, well, I know what you're thinking next is, what if my file is bigger than this number that you gave on the screen, which is 4144 kilobyte? What do I do then? I don't think my entire wedding video would fit into this 4144 kilobyte size. It's definitely something bigger than this. So what's next? But along with this what's next question, I'm sure that you are also thinking that now definitely we can just keep extending the same approach, saying that the last entry of each block is to the new block of pointers, and so on and so forth, right? We can have this, it is not called two-level index, but this approach is called multi-level index. And what's the con of that? Well, in this case, we have to parse through each level. So now if we just, the levels that we are visualizing is horizontally, make it vertical, flip it around, then you would see that what we are doing is we have this one level, then we have few entries for this one level, but then we have the last entry of this level that stores the list of pointers. So again, we have few entries of this one level, and then we have the last entry of this level that stores the list of pointers. So it's basically an imbalanced tree data structure. And this imbalanced tree is good in a way that it gives us approach to accommodate larger files, but it also has its own disadvantage in the sense that when we want to access the file, we would have to parse through all this level of indirections or all this multiple levels of this multi-index structure. And small other optimization that we could do is, well, rather than just sparing my last, I know that if my the average size of files is big in the data that I'm storing on the system, then rather than, why should I just spare the last entry to store the list of pointers? Why not last two entries to store the list of pointers? In that case, we could minimize the number of levels that we have in this multi-level index, right? Yes, definitely we could do that. And we could call that as triple indirect pointers, where we have two entries just reserved to store this list of pointers. So on and so forth, we can keep increasing this to make a design to reach a sweet point, which is just best to accommodate the requirement that we have. So multi-level index is a generic approach. Again, it has many variables which could be tweaked and configured particularly to the requirement of what data is being stored on that system, or what are we using this file system to, what type of data are we using this file system for. Now, some of the popular existing file system that are designed with this concept of storing data with multi-level index are ext2, ext3, and I'm not sure if you're familiar with NetApp company, but NetApp company has its own file system called as WAFO. That is also underneath that also uses multi-level index to map to its data from inodes. Now, with this multi-level index, do we solve all our problems?